Hi guys, the measured speed is a clue. It is not a number pulled from thin air. It is a fingerprint of an origin story that began around another star and played out across our entire galaxy when astronomers first tracked the path of the object now called 3I/ATLAS. They found that it was already moving at roughly 61 kilometers per second with respect to the Sun, which is a little more than 220,000 kilometers per hour. That velocity is not a brief burst from jets or an engine. It is the natural consequence of how gravity shapes the motion of a body that fell into our neighborhood from interstellar space on an unbound path. As it plunges deeper into the solar gravitational well, it accelerates. As it climbs out, it will decelerate, keeping the same excess speed far from the Sun that it had before it arrived. That is what a hyperbolic trajectory means. It is the signature of an object that does not belong here. This is only the third confirmed interstellar visitor ever seen crossing our planetary system. It was discovered in the first days of July of the year 2025 by the Asteroid Terrestrial Impact Last Alert System at the Rio Hurtado site in Chile. From the start, its path showed that it came from beyond the sphere of the planets. The National Aeronautics and Space Administration emphasizes two practical facts right away. First, there is no danger. The minimum distance to Earth will be about 1.8 astronomical units, which is on the order of 270 million kilometers. Second, the comet will reach its closest point to the Sun around late October of the year 2025 at about 1.4 astronomical units, just inside the orbit of Mars. Those numbers fix both the safety question and the observing calendar. To understand why the speed exceeds 200,000 kilometers per hour, we need a clean mental model. Think of three linked pieces. One is the energy story. The second is the frame of reference. The third is the origin of the object's inbound motion before the Sun took over. Energy first. Far from the Sun, where solar gravity is weak, the interstellar object traveled through the local galactic neighborhood at essentially constant speed. As it fell inward toward the Sun, gravitational potential energy converted into kinetic energy. That is why its heliocentric speed rose from tens of kilometers per second to more than 200,000 kilometers per hour as it moved inward. At the Sun's closest approach, the speed peaks. Thereafter, it gives back the borrowed energy and slows, asymptotically returning to the same interstellar cruising speed it had before arriving. In orbital mechanics, this constant is called the hyperbolic excess velocity. For 3I/Atlas, early solutions based on the growing data arc found that excess to be around 58 kilometers per second. With nothing but solar gravity acting, that number barely changes. It is the interstellar pedigree, written in units of motion. Now, the frame of reference. You can measure the speed relative to Earth, relative to the Sun, or relative to a conceptual frame called the local standard of rest. The commonly quoted value here is relative to the Sun. That is the measurement that matters for a path through our system, and it is why the speed is more than 200,000 kilometers per hour at discovery and higher still near perihelion. In everyday terms, it is moving faster than any natural object bound to the Sun at Earth's distance. Only a specialized spacecraft skimming the solar atmosphere has gone faster. The Parker Solar Probe, during a record perihelion in late December of the year 2024 reached roughly 690,000 kilometers per hour relative to the Sun. That dramatic comparison shows the scale of the numbers we are talking about. The comet is not a spacecraft, but its speed is in the same league as the fastest human-made object when gravity is doing all the work. Where did that excess speed come from in the first place? For that, we have to leave the solar system entirely and look at how small icy bodies are launched into the galaxy. The current consensus, shaped by observations of planetary systems and by dynamical models, is that most interstellar objects begin as planetesimals in their home systems. When giant planets form, they scatter enormous numbers of these building blocks. Some are thrown inward and destroyed. Some are slung outward and escape. In a young system with multiple massive planets or within a crowded stellar nursery, ejection becomes efficient. Those bodies drift into the galactic population of wanderers that every so often pass near the Sun. Reviews over the past few years outline the mechanisms clearly and predict that the galaxy should teem with such fugitives from planet formation. 3. I/ATLAS is the newest direct sample. What makes 3I/ATLAS especially interesting is that its motion carries a clue to the kind of stellar neighborhood it came from. A modeling analysis published in July of the year 2025 set the object in the context of a galactic population model built from Gaia star data. The kinematics of the comet as it approached the Sun match expectations for objects that come from the Milky Way's thick disk, a galactic component rich in ancient stars that tend to have larger random velocities relative to the Sun. The same study used that connection to infer a likely age greater than 7.5 billion years, with the possibility that the material in this comet predates our solar system by billions of years. If that inference holds, the high speed we see today is partly a fossil of the hotter, more dynamic early Milky Way, as well as the exuberant scattering inside the comet's birth system. Motion and history are bound together. New work tracks the comet back through our region of the galaxy and finds a busy history by numerically integrating the orbit of 3I/Atlas together with the motions of tens of millions of nearby stars from the Gaia catalogue. One team identified on the order of 24 close stellar passages within roughly 1 parsec over the last 10 million years. That result does not point to a single parent star. Instead, it shows how an interstellar body can pick up small nudges over vast times as it threads the labyrinth of local stellar gravity. The speed we measure now is the vector remnant of ejection long ago, plus the cumulative whispers of the galaxy since. While dynamics tell us about past motion, composition hints at where in a planetary system 3I/ATLAS formed. Spectroscopy with the James Webb Space Telescope in early August of the year 2025 captured the object's spectrum with the near-infrared spectrograph instrument. The first reported results show a coma dominated by carbon dioxide relative to water, with a carbon dioxide to water ratio around 8:1, among the highest ratios ever measured in a comet. That ratio can be produced if the nucleus formed far from its star near the carbon dioxide ice line, or if the outer layers were processed by radiation over a long time in interstellar space. Either way, the extreme chemistry adds to the case that the object is old and that its present swift passage carries material records from a different stellar nursery. The cloud of facts about this object is expanding quickly because many eyes are on it. The Hubble Space Telescope imaged the comet in late July of the year 2025 and revealed a tear-shaped envelope of dust surrounding the nucleus. Those data gave the first firm size constraints, placing the nucleus somewhere between roughly 440 meters and about 5 6/10 kilometers across. That range matters when we ask whether outgassing could meaningfully alter the object's path or speed. For a nucleus that large, the non-gravitational push from jets of gas and dust can curve the trajectory slightly, but it cannot supply the tens of thousands of kilometers per hour needed to create the measured hyperbolic excess. Gravity set the baseline speed. Comet jets only fine-tune the track. Even before discovery, telescopes had captured the traveler by chance. The Transiting Exoplanet Survey satellite recorded the comet in May and June of the year 2025, more than 7 weeks before the alert. Researchers stacked those images to tease out a faint signal and reported a gradual brightening as the comet crept inward. That paper is valuable for speed because it added early astrometry to the orbit fit and cited a hyperbolic excess velocity around 58 kilometers per second. It also gave a rare first. This is the first time that the Exoplanet Hunting Telescope caught an interstellar object in pre-discovery data. The National Aeronautics and Space Administration has assembled a long list of observers across the fleet. Hubble continues to monitor. The James Webb Space Telescope has already observed the object. The new spectrophotometer for the history of the universe, Epoch of Rhionization and ICES Explorer, observed it in August of the year 2025. Mars orbiters and rovers will try to capture it near the Mars Encounter window. Even spacecraft nearer to the Sun, such as the Parker Solar Probe and heliospheric imagers, may add unique vantage points when geometry permits. The result is a coordinated experiment in how to extract the maximum science from a fast and fleeting visitor. The speed also sets the rhythm of observation. Because of the geometry of the encounter, the comet passes behind the Sun from Earth's viewpoint during the weeks around perihelion. For ground-based telescopes, there will be a pause and then a return of visibility in early December of the year 2025. That schedule is not a curiosity. It is a direct consequence of the path and the high inbound speed. On a slower, wider swing, we might have had a longer observing window from Earth. On this faster dive, the best chance to study peak activity falls to eyes elsewhere in the solar system. When you compare 3I/ATLAS to the previous two interstellar objects, the role of speed becomes even clearer. The first, 1I/Oumuamua, whipped around the Sun in September of the year 2017 with a maximum speed near 87 kilometers per second at perihelion, but its excess speed far from the Sun was closer to 26 kilometers per second. The second, 2I/Borisov, behaved more like a familiar comet and cruised through at about 177,000 kilometers per hour relative to the Sun, with an excess speed around 32 kilometers per second. 3I/Atlas came in hotter, with a measured excess around 58 kilometers per second and a discovery speed of roughly 221,000 kilometers per hour. That ranking reflects different histories. Each object left a different star under different circumstances and then spent different spans of time being stirred by the galaxy. How does an interstellar object end up with an excess of 50 plus kilometers per second? One part is the kinematic lottery of the galaxy. Our Sun is on a nearly circular path around the Milky Way. Nearby stars and small bodies have their own random motions layered on top of that vast rotation. When a free floating object approaches the solar system, the relative speed depends on how its motion vector lines up with the Sun's. If it happens to be moving roughly with the Sun, the excess can be modest. If it comes from a direction that subtracts little and adds much, the excess can be large. That is the simplest piece. A second part is the launch from the home system. In a young planetary system, a planet the mass of Jupiter or more can fling a small body outward at several kilometers per second relative to the star. In a binary star system, a close passage can add still more. Those ejections do not need to supply dozens of kilometers per second by themselves. They only need to push the body past the escape speed of the system. The rest of the excess a visiting observer measures later comes from the difference between the stellar motions. Reviews of interstellar objects and exocomets make this point explicitly. The speeds we see in our sky are the vector sum of two systems' motions, not evidence of engines. A third part is the galactic environment. Over billions of years, a small body wanders in and out of giant molecular clouds, past star-forming regions, and through tidal fields that slightly reshape its path. Individual encounters with stars at a distance of a fraction of a parsec add tiny nudges. A recent analysis found roughly 24 such close passages for 3 I/ATLAS over 10 million years. That accumulation does not tend to slow an object in any systematic way, but it does broaden the distribution of speeds and directions that we observe when one eventually passes by the Sun. Seen this way, the more than 200,000 kilometers per hour is a time averaged monument to its long walk across the galaxy. There is an important limit to keep in mind. Cometary outgassing can add small, non-gravitational forces. It can act like a set of asymmetric thrusters. In the case of Oumuamua, that subtle push explained a puzzling change in motion without invoking exotic materials. For 3 I/ATLAS, outgassing will surely matter for precision orbit fitting, but the magnitude of those forces is tiny compared to the gravitational energy exchange with the Sun. You can estimate this by comparing the momentum carried by typical gas production rates to the momentum represented by a nucleus that is hundreds of meters to a few kilometers across, moving at tens of kilometers per second. The numbers differ by orders of magnitude. The right conclusion is this: outgassing tweaks the course. Gravity sets the speed. High speed also reshapes the observing problem into a logistical race. The list of space assets matters because the best angles and the best solar elongations do not always happen for Earth observers. The European Space Agency has noted that its Mars Express and the ExoMars Trace Gas Orbiter will attempt observations near the time when the comet passes closest to Mars in early October of the year 2025 at a separation of roughly 30 million kilometers. other teams have explored opportunities for spacecraft farther out. Some analyses even consider whether images like those on the Parker Solar Probe and heliophysics missions could capture the comet's tail against the interplanetary background during the critical weeks when Earth cannot. Every successful observation tightens the orbit solution and refines the speed we quote. Like any fast story, this one develops quickly. The same National Aeronautics and Space Administration page that gave the first public primer has been adding confirmed facts as they arrive. It lists the expected return to Earth visibility in early December of the year 2025. It lists the safe distances. It points to a growing multimedia archive, including a trajectory diagram generated by the Jet Propulsion Laboratory and image galleries. It even highlights the education-ready takeaway that this comet is an opportunity to explain what a hyperbolic orbit really is. The premise is simple and powerful. An object that is moving too quickly to be captured by the sun's gravity will not loop around. It will pass and go. That is why the target is a once-only opportunity. Composition and speed intertwine again in the Webb results. A coma with carbon dioxide outgassing greater than water by a factor of about 8 suggests either formation in an especially cold outer disk region, or a surface that has been altered by radiation and micrometeoroid gardening during a very long interstellar voyage, or both. Either way, such an ice recipe influences how quickly the coma rises with solar heating and how the dust tail responds to solar radiation pressure. That in turn affects how easily images on spacecraft or from Earth can track the motion of the coma versus the motion of the nucleus. It is not just a chemistry footnote, it is a tactical detail in the observing campaign and a structural clue to the comet's birthplace. The most striking visual so far comes from Hubble, which shows a compact teardrop envelope around the nucleus. In August, mission scientists used those images to bound the nucleus size and to describe the dust cocoon in plain language. That shape is a reminder that what we watch move at extraordinary speed is a fragile assembly of ices and dust grains that survived ejection from a distant star system and the long trip through the galaxy. The engineering feat here is nature's. A weakly bound rubble of ice has held together long enough to be seen by us and measured. Then it will vanish back into the dark. Why does the speed matter for the story we tell about our own origins? Interstellar comets do not merely pass by as curiosities. Their velocities, directions, and chemistry constrain how planetary systems form and clear themselves. When you assemble the statistics of many visits, you learn about how common giant planets are, about how efficiently different kinds of systems eject material, and about how the galaxy stirs those relics over time. The current discovery cadence and recent population modeling even suggest that there is almost always at least one interstellar object somewhere inside the solar system, just usually faint and hard to find. 3I/ATLAS, by being bright enough and fast enough at the right time, becomes a touchstone for that larger picture. All of this returns us to the original question: why does 3I/Atlas move at more than 200,000 kilometers per hour, and what does that say about its past? It moves that quickly because it came from far outside the sun's gravitational reach with a substantial interstellar cruising speed, probably inherited from a star in the Milky Way's thick disk. That excess speed, set by its ejection and by the random velocities of stars in our part of the galaxy, was then amplified on approach to the Sun by the straightforward conversion of gravitational potential energy into kinetic energy. The number we recite is not arbitrary. It is the combined product of a launch during a violent phase of planet formation, a long drift through the galaxy with many small stellar encounters, and a final sprint down the solar gravitational slope. The comet's chemistry now argues that it formed far from its star in a cold region rich in carbon dioxide ice. The kinematics argue that the parent system belongs to an older, dynamically hotter stellar population. The end result is a compact body that carries ancient information and travels quickly enough to demand our attention for a short time and then depart forever. There is one more lesson in the numbers. A natural object moving at more than 200,000 kilometers per hour is not surprising in a galaxy where the Sun itself speeds around the center at hundreds of kilometers per second. What is surprising is that we can now spot such a traveler early, triangulate its speed with exquisite precision, and point multiple spacecraft and telescopes to catch it on the fly. That capability turns speed into science. With 3 I/ATLAS, every kilometer per second that we measure and every spectral line that we trace helps decode a story that began around another star and took a billion-year detour through the Milky Way to reach our cameras. That is why its velocity is a clue and not just a headline. It tells us that the small cold things that seed planets in other systems do not stay put. Some of them cross the void, and once in a while one screams past our Sun, reminding us that planet-making is a galactic process and that even a single number can carry the memory of a very long journey. For night science stories, the takeaway is crisp. The high speed is the proof and the map. It proves the comet is unbound. It maps a likely ancestry in an old, fast-moving stellar population and a birth zone far from a distant star where carbon dioxide ice was abundant. It connects the gravity we can calculate, the chemistry we can observe, and the galactic dynamics we can model into a single narrative we can watch unfold over months. The clock runs quickly on this visitor, but the message is slow and deep. The small bodies that build planets are not confined to one sky. They travel. They carry their histories in their motion, and sometimes their speed is the simplest way to read their past. What we do not know is a long list, and each item maps to a specific observing tactic. The nucleus is still unresolved. The sharpest images from the Hubble Space Telescope constrain its diameter to be no smaller than about 440 meters and no larger than about 445 meters, about 5 6/10 kilometers, a range that straddles 2 orders of magnitude in mass, depending on the density you assume. That is not a cosmetic uncertainty. Mass controls how easily sunlight-driven jets can torque the body and alter its path. The only path to narrow this window is continued high-resolution imaging when the geometry improves after the object re-emerges from behind the Sun in early December of the year 2025, and careful modeling of how the dust coma's brightness profile blurs the point-like nucleus in those images. That is exactly what the Hubble program says it will do once the target returns to safe elongations. We do not yet have a secure rotation period or a firm direction for the spin axis. A slow rotation hides under the light of even a faint coma. Early photometry found only low amplitude brightness changes, and in some data sets no convincing periodicity at all, which is typical when a dust coma damps the nucleus signal. One detailed study with the 10-meter class Gran Telescopio Canarias reported a period close to 17 hours with a small brightness amplitude that shrank as activity grew through July, which is exactly what you expect if newly released dust increasingly veils the bare nucleus. As a cross-check, independent teams using the Transiting Exoplanet Survey Satellite pre-discovery stacks reported no statistically strong periodic signal across about 20 days of coverage, again consistent with a weak nucleus modulation washed out by coma light. The way forward is straightforward. Keep building a multi-month light curve from large telescopes and solve for a rotation period that stays stable across filters and instruments. Use structure in the dust fans that point sunward in the Hubble and Very Large Telescope images as tracers of active areas to infer pole direction. If the pole solution is real, it will predict a seasonal pattern in jet direction that can be tested on the post-perihelion leg. The composition story is both exciting and unfinished. The first near-infrared spectra from the James Webb Space Telescope on August the 6th of the year 2025 show a coma dominated by carbon dioxide, with water present at much lower abundance, along with detections of carbonyl sulfide, water ice, carbon monoxide, and dust. The carbon dioxide to water mixing ratio sits near 8:1, which is among the highest values ever measured in a comet, and stands well above the trend established for long-period comets observed at similar solar distances. That number has real interpretive power. It points either to formation near the carbon dioxide ice line in a very cold outer disk, or to a surface that has been processed in space so that heat penetration is insufficient to liberate much water relative to carbon dioxide. But we have only a first look. We do not yet know if this ratio will hold as the object warms, or whether it will pivot toward a more familiar water-dominated coma closer to the Sun. The plan to answer this is to take repeated spectra with the James Webb Space Telescope and with ground-based instruments after reappearance to map how the volatile mix evolves with heliocentric distance. The spectrophotometer for the history of the universe. Epoch of Rayonization and ICES Explorer has already mapped an extended carbon dioxide envelope hundreds of thousands of kilometers across, so matching those global maps to the point source spectra from the James Webb Space Telescope will be one of the next clean tests. Even the most basic molecule in cometary science, water, arrived with a surprise. Ultraviolet imaging with the Neil Gehrels Swift Observatory detected hydroxyl emission beyond 3 astronomical units, implying ongoing water production at an unusually large distance. That calls for a mechanism beyond pure sun-warmed surface ice. One plausible picture is that larger icy grains lofted from the nucleus sublimate in the coma and act as an extended secondary source of water. To confirm or refute that picture, observers will combine ultraviolet tracers of hydroxyl with thermal infrared monitoring of large coma grains and with optical spectroscopy of cyanide and other radicals that rise as water-driven activity strengthens. The balance among hydroxyl, carbon dioxide, carbon monoxide and cyanide will be one of the crispest diagnostics for what drives the comet now and how that driver changes with time. The visible color and the dust physics carry their own unknowns. Early Very Large Telescope spectroscopy in the first week of July showed a red and featureless continuum redder than many familiar comets and closer to the colors of some trans-Neptunian objects and the centaur named Pholus. That already hints at a dark, complex organic surface and fine dust grains. But polarimetry, which measures how the scattered light is oriented, delivered the sharper shock. A coordinated campaign with the Very Large Telescope, the Nordic Optical Telescope, and the Bulgarian Rozhen Telescope found an unusually deep and narrow negative polarization branch at small phase angles, reaching a minimum near -2 7/10% and switching sign near 17 degrees. That combination has not been seen in other comets and even differs from the previous interstellar comet named 2I/Borisov. Negative polarization at small angles often signals compact submicron grains with particular surface textures or mixtures of ice and darker organics. But the exact mix that reproduces this deep branch is still unknown. The way to settle it is to build a full polarimetric phase curve across as wide a range of scattering angles as the geometry allows, and to combine that with mid-infrared measurements of the silicate feature shapes that betray grain size and porosity. That program is underway across multiple observatories. The green question is unresolved. Photographers recorded an emerald tint in mid-September images, and cyanide has been spectroscopically detected, which is one known path to green glows in comets, along with the more common dicarbon bands. But other groups report no clear sign of dicarbon yet, and color imaging can mislead when filters and processing differ. Here, the standard is simple. Confirm the presence or absence of the key emissive molecules with spectroscopy. Optical spectra from the Very Large Telescope show cyanide at heliocentric distances as large as just over 3 astronomical units and do not yet show dicarbon. That argues for a cautious description. If the green persists and dicarbon remains absent, then cyanide and possibly oxygen atoms could be the dominant contributors to the tint. If dicarbon emerges later, the color story will change. Either way, the fix is to keep taking medium-resolution spectra across the relevant bands as the object brightens and as the dust coma grows. Another open issue is the scale and direction of non-gravitational acceleration. Outgassing can act like asymmetric thrusters and nudge the trajectory. In the previous interstellar object named 1I/Oumuamua, this effect was the center of a long debate because the acceleration was strong and chemically puzzling. For 3I/Atlas, the expectation from comet physics is that the effect should be modest for a kilometer-scale nucleus, likely below the threshold that could be robustly identified in early astrometry. The way to know is to wait for a longer arc of precise positions taken before and after perihelion, then fit standard outgassing parameters and see whether the residuals shrink. The small body database at the Jet Propulsion Laboratory will fold in non-gravitational terms only when the data justify them. That is a measurement to watch in December and beyond. We have only a provisional grip on how the comet's chemistry is changing with time. By mid-August, the Very Large Telescope team reported a dramatic rise in neutral nickel line emission and the first solid detections of cyanide, while water and oxygen lines remained faint at large distances from the Sun. The question is whether that early heavy atom signature marks unusual release mechanisms from the dust, or whether it is simply a sensitivity effect that vanishes once water and dicarbon flood the coma at smaller heliocentric distances. Repeated high-resolution spectroscopy at different distances and solar phase angles will give the answer. The key is to measure how nickel and cyanide production rates scale relative to water and carbon dioxide and compare those scalings to solar system comets. We also do not yet know the internal structure. Is the nucleus a compact monolith with a thin refractory crust or a porous rubble assembly with many small vents? Disentangling that is not photogenic, but it is doable. It requires connecting the time variability of the coma morphology with thermophysical models that include heat diffusion, sublimation fronts, and changes in tensile strength as the material cyclically warms and cools. In practice, that means measuring the timescale on which jets turn on and off as local sunrise and sunset sweep across the surface, and matching that to model predictions that depend on porosity and thermal inertia. Hubble images from late July show a clear sun-facing plume and the hint of a developing anti-solar dust tail, which gives the first pieces of that timing puzzle. More images after perihelion will sharpen the constraints. No one has yet measured the deuterium to hydrogen ratio in water vapor from this object, which would be a major clue to its formation temperature and heritage. The James Webb Space Telescope instruments can, in principle, detect the deuterated waterlines if the coma is bright enough and if the geometry cooperates, but the signal is faint and the object will be behind the Sun for Earth observatories right at peak activity. Sub-millimeter facilities that are powerful for isotopic work will face the same geometry problems and the additional challenge of a distant, relatively faint target. The near-term plan is therefore indirect. Measure stable isotopes where they are more accessible, such as the ratio of carbon-13 to carbon-12 in cyanide bands, and compare to solar system values. If those come back unusual, they will strengthen the case for a distinct formation environment, even without a definitive water isotope measurement. The dynamical origin remains debated. One analysis that extrapolated the inbound velocity relative to the local standard of rest concluded that the object fits the kinematic profile of the Milky Way thick disk and could therefore be very old, perhaps older than 7.5 billion years. A separate study that looked at a control sample of stars with similar three-dimensional velocities argued that thin disk membership is more likely. A third approach integrated the orbit backward against the motions of nearby stars and found some 24 passages within about 1 parsec across the last 10 million years, which is enough to scramble any clean trajectory back to a specific parent star. This is not arm-waving. Each claim is testable as the orbit and the chemistry become better constrained. A thick disk heritage would predict an overall older, lower metallicity chemical signature. A thin disk origin would fit a wider range of compositions. The plan to make progress is to combine precise post-perihelion astrometry with the growing spectroscopic inventory and ask whether the kinematic and chemical priors point to the same galactic population. There is also the matter of how early activity began. Pre-discovery stacks from the Transiting Exoplanet Survey satellite reveal the object in May, many weeks before the alert, and the brightness evolution suggests it may have been active at a solar distance near 6 4/10 astronomical units. A separate team used archival data from the Zwicky Transient Facility to push the activity limit even farther back. If activity truly started beyond 6 astronomical units, the driver cannot have been water. Carbon dioxide and carbon monoxide are the prime candidates. That is consistent with the James Webb Space Telescope carbon dioxide dominance and with the spectrophotometer for the history of the universe. Epoch of Rhionization and ICE's Explorer detection of an extended carbon dioxide coma. The observational path forward is to keep pairing wide-field infrared mapping of the global carbon dioxide envelope with point source spectroscopy that isolates the volatile mix close to the nucleus. That combination will tell us how the activity source terms feed the expanding coma. The observational cadence itself is a scientific constraint. Around late October of the year 2025, the comet is almost behind the Sun as seen from Earth. That blackout for ground-based observers falls tantalizingly close to perihelion. It means the most intense phase of near-solar heating must be covered by spacecraft at other vantage points. The Parker Solar Probe's Wide Field Imager, formerly the Wide Field Imager for Solar Probe, is expected to have a window from late September into early November to catch the dust environment against the inner heliosphere, just when terrestrial telescopes cannot. The European orbiters at Mars aim to observe around the early October closest passage at a distance of roughly 30 million kilometers. Jupiter missions and outer heliophysics imagers will also attempt rides along. The practical point is clear. A coordinated fleet is the only way to fill the perihelion gap. After that, Earth-based telescopes and the Hubble Space Telescope resume the watch in early December. We do not yet know whether the nucleus will fracture. Many comets fragment under thermal and rotational stresses. The perihelion distance of a little over 1 3/10 astronomical units is not a recipe for catastrophic heating by itself, especially compared to sun grazers. But the torques from asymmetric outgassing can spin up a small body to the point of structural failure. The signs to monitor are abrupt jumps in brightness, followed by a change in the coma morphology and the appearance of condensations in high-resolution stacks. If that happens, the follow-up will be immediate. Spectra will look for freshly exposed ices and astrometry will try to track fragments. If it does not happen, that non-detection is valuable too. It sets a lower bound on cohesion for an interstellar nucleus, a number that can be compared to values inferred for long-period comets born in our own distant cloud. Brightness predictions are another open thread. Through mid-September, the object began to brighten faster than a simple power law would forecast, which could be a pre-perihelion flare-up or simply the point where carbon dioxide-driven activity transitions to a mixed regime. Amateur and professional photometry will keep logging the secular light curve. The specific test is whether the post-perihelion fading follows the usual hysteresis pattern seen in many comets, where the outbound light curve does not simply track the inbound one in reverse. That asymmetry tells you about thermal lag and layering in the nucleus, which in turn links back to how it formed. We also lack a firm dust-to-gas ratio and grain size distribution. The height and shape of the 10 micrometer silicate feature and the slope of the mid-infrared continuum are the classic tools, and observers will try to get them with the James Webb Space Telescope and with large ground-based facilities in the months after reappearance. Those measurements, combined with the optical polarization curve, can pin down whether the dust is dominated by compact submicron particles or by fluffy aggregates, and whether ice-coated grains make up a significant fraction. The answer matters because dust-carrying embedded volatiles is a natural way to reconcile distant water detections with a carbon dioxide-dominated gas phase close to the nucleus. A crisp statistical question remains open. How common are objects like this in our skies at any given time? Detection of the third interstellar body in less than a decade suggests that at least one such object is usually within the solar system at any moment, yet most are too faint to spot. Population models will be updated with this detection and with the vetted selection function of the surveys that found it. But the most incisive inputs will come not from the discovery itself, but from the measured speed distribution, chemical fingerprints, and the rate of changes near perihelion. Each of those will feed the next generation models of planet formation and ejection in other stars, systems. There is a communications question as well. Claims of exotic behavior will continue to surface. The antidote is measurement. The deep negative polarization is a measured optical property that can be compared against a library of solar system bodies. The carbon dioxide to water ratio near 8:1 is a measured value from a well-calibrated spectrograph. The early hydroxyl detections are measured in ultraviolet imaging. The cyanide lines are measured in optical spectra. When those numbers are combined with a consistent orbit fit and with post-perihelion non-gravitational parameters, the room for speculation shrinks and the physical picture grows. That is how this field advances. A brief inventory of the key unknowns and the instruments that will address them helps frame the next few months. The range of allowed nucleus diameters will tighten with Hubble imaging and with refined coma modeling in December and January. The spin period and pole direction will be solved by a combination of long baseline light curves and jet morphology fits, with results checked against any seasonally modulated activity. The carbon dioxide dominance versus water rise will be traced by repeat near-infrared spectra with the James Webb Space Telescope and by wide-field carbon dioxide maps from the spectrophotometer for the History of the Universe, Epoch of Rhionization, and ICES Explorer. The negative polarization curve will be extended and compared to silicate feature shapes in the mid-infrared for grain size and porosity constraints. The cyanide and nickel production rates will be tracked against water and carbon dioxide to test for unusual heavy atom release. The non-gravitational acceleration will be fitted once the post-perihelion astrometry fills in the long arc. The dynamical origin question will be revisited as the refined orbit is run backward through the field of nearby stars and checked against thick disk and thin disk priors, and the perihelion gap will be partly bridged by the Parker Solar Probe Wide Field Imager and by Mars orbiters, whose observing plans are already public. What we may never know is worth stating plainly. We may never identify the exact parent star. The cumulative nudges from passing stars and clouds over billions of years erase the precise trail. We may never pin down the deep interior layering without an occultation or a serendipitous split, and we may not get the gold standard water isotope ratios unless the coma becomes much richer in water than it is today. But even with those limitations, the dataset will be exceptional. This is only the second time we can watch an interstellar comet behave like a comet, not an inert shard. The specific chemistry and the specific speed make it a case study in planets forming elsewhere. The tactical timeline is clear enough to plan around. Through late September and October, the object slides into solar conjunction for Earth, and the best hope for continuous coverage lies with images aboard spacecraft in the inner solar system and at Mars. Around late October, it reaches perihelion. By early December, it returns to view for ground-based telescopes and for the Hubble Space Telescope. The James Webb Space Telescope can then schedule follow-on spectra to capture the outbound composition. That is when many of the unknowns listed here will begin to shrink. There is value in tests that fail. If the cyanide lines level off while the overall brightness continues to grow, that calls for a change in the chemistry model. If the negative polarization minimum shifts with time, the dust grain mix is not static. If the non-gravitational terms never rise above noise, that tells us the outgassing thrusts are weak and probably symmetric in the aggregate. If water stays a secondary player even much nearer to the Sun, the case strengthens for formation in a very cold outer disk far from a parent star, or for an insulating crust that redirects heat. And if the post-perihelion light curve does not mirror the inbound curve, it will illuminate how layers in the surface respond to the Sun. One lesson of interstellar visitors is that impatient stories age poorly. The numbers you want most arrive last. That is the nature of orbital geometry and of signal to noise. For 3I/ATLAS, the mission briefs are already public. The National Aeronautics and Space Administration list of participating assets includes the Hubble Space Telescope, the James Webb Space Telescope, the Transiting Exoplanet Survey Satellite, the Swift Observatory, the Spectrophotometer for the History of the Universe, Epoch of Rionization, and ICES Explorer, and a roster of planetary and heliophysics spacecraft from Mars to near the Sun. Those eyes will do exactly what you would design for this target. They will gather spectra across the volatile bands, map the global carbon dioxide envelope, trace the dust polarization with phase angle, and fill the perihelion gap from vantage points Earth cannot reach. They will then hand the target back to Earth-based telescopes for the long outbound watch, when non-gravitational terms can finally be fitted and residuals finally inspected. So the state of knowledge is this. We know the speed is high and interstellar, and we know the orbit will carry the object out for good. We know the coma is anomalously rich in carbon dioxide, that water appears even far beyond 3 astronomical units, that cyanide and neutral nickel have appeared in the spectra, and that the dust polarization is unusually negative at small angles. We do not yet know the precise size, the rotation period and pole, the dust grain size distribution, the dust-to-gas ratio, the deuterium to hydrogen ratio, the level of non-gravitational acceleration, the risk of fragmentation, or the exact galactic population to which the parent system belongs. Each unknown is paired to an imminent measurement. That is why this interstellar comet matters scientifically. It is not a single headline. It is a schedule of tests. Over the next few months, the answers will arrive in the form of repeated spectra, longer light curves, new images from different vantage points, and a refined orbit solution. That is how we will turn a fast stranger into a well-constrained data point for how planets form across the Milky Way. Counting visitors is not a matter of collecting souvenirs. It is a matter of rates and biases. We have seen only 3 confirmed interstellar objects in 8 years. That small tally says more about our limited reach than about the galaxy's supply. 3I/Atlas was confirmed in early July of the year 2025 as the 3rd such visitor after 1I/Oumuamua in the year 2017 and 2I/Borisov in the year 2019. Each one was found by a wide field survey that happened to be looking in the right direction at the right moment. The pace of confirmed discoveries is therefore not the true cadence of flybys. It is the cadence of our instruments catching up. A cleaner way to think about frequency is to start from the physics and the stellar motions around us. When you combine the typical space velocities of nearby stars from the Gaia catalogue with gravitational focusing by the Sun, you can predict how many unbound bodies should sweep through the inner system, regardless of whether we notice them. That calculation gives a simple headline number. On average, about 7 interstellar objects pass within 1 astronomical unit of the Sun every year. The velocity distribution is skewed toward moderate speeds. Roughly 92% arrive with speeds below 100 kilometers per second at infinity relative to the Sun. Only a small fraction form a high-speed tail. In addition, that same modeling predicts a demographic mix tied to galactic structure. The vast majority should come from the Milky Way thin disk, a few per decade from the thicker and older disk population, about 1 per decade from the halo, and only a few per century from objects unbound to our galaxy. Those numbers give context for 3I/ATLAS. It is statistically normal to have 1 or more interstellar bodies passing through the inner solar system every year, even if our telescopes do not see them. So why have we seen so few? Detection is hard for 3 practical reasons. First, these bodies are small and dark. A typical object the size of Oumuamua is far fainter than the survey limits until it is already near the Sun and moving fast. Second, geometry matters. Many pass through at low solar elongation, where ground-based telescopes cannot look without washing out the signal in scattered sunlight. Third, motion itself is a penalty. A long exposure smears a fast target into a streak and lowers the detection significance, a phenomenon called trailing loss. Survey simulations that include these effects predict a very uneven harvest depending on how deep and how often a given telescope scans the sky and which parts of the sky it emphasizes. The optimal hunting grounds cluster around the solar apex and anti-apex directions where relative motions line up to boost discovery odds. The upgrade that changes the statistics is the Legacy Survey of Space and Time at the Vera Rubin Observatory. Several independent studies have quantified what a deeper, faster, wider survey will do. One peer-reviewed analysis projects roughly 15 interstellar objects in 10 survey years under conservative assumptions and notes that this is likely a lower limit because the true size distribution is still uncertain. A separate synthetic detection study found that the yield could range from essentially 0 to roughly 70 per year, depending on the albedos and the slope of the size-frequency distribution. At the recent joint meeting of the Europlanet Science Congress and the Division for Planetary Sciences, survey specialists presented updated simulations that bracket the Rubin yield between roughly 6 and roughly 50 interstellar objects over the core survey, again highlighting the sensitivity to unknown population parameters. The spread in those forecasts is not a problem. It is a prediction we can test as soon as the survey starts operating at scale. Before Oumuamua, the best we could say came from null results. A careful analysis of years of Pan-STARRS and allied surveys set an upper limit on the space density of kilometer-class unbound objects. That ceiling turned into an estimate once Oumuamua appeared, and a widely cited calculation inferred a number density on the order of a few tenths per cubic astronomical unit for Oumuamua-sized bodies. That value implied a surprisingly large total mass in interstellar planetesimals, unless most stars contribute substantially, a clue that galactic recycling of planet-building leftovers is vigorous. The first limit told us only that such bodies are not extremely common at large sizes. The first detection told us that smaller ones may be common enough that, with better surveys, we should see a steady stream. 2I/Borisov and now 3I/Atlas sharpened that picture, but the uncertainties remain large because 3 data points do not fix a population. The other end of the size spectrum tells a different story about frequency. We are bathed in a continuous stream of interstellar dust. Spacecraft have measured it in situ for decades. Ulysses detected the flow of micrometer-scale grains plunging through the heliosphere during the 1990s and 2000s. Cassini sampled interstellar grains in the inner solar system and even inside the orbit of Earth. Those measurements are not the same as seeing a discrete comet, but they demonstrate a persistent flux of extrasolar material crossing our planetary space at characteristic speeds of a few tens of kilometers per second. On that microscopic scale, interstellar visitors are not rare at all. They are background. What about larger interstellar meteors that burn up in our atmosphere? One candidate fireball from early January of the year 2014 was later cited by the United States Space Command as having sufficiently high speed to imply an unbound orbit based on classified tracking data. At the same time, multiple independent reviews of meteor catalogues caution that measurement errors can easily push ordinary bound meteoroids into seemingly hyperbolic solutions, and that robust, confirmed cases are therefore exceptionally rare. The correct takeaway is cautious. There may be occasional interstellar meteors, but present radar and optical networks are not yet precise enough to quote a reliable rate. This uncertainty does not weaken the case for frequent macroscopic visitors within the inner solar system. It simply underscores that confirmation thresholds differ between a tractable orbit found by many telescopes and a brief atmospheric flash measured with large uncertainties. Turn back to the practical question for planning observations and missions. If roughly 7 interstellar bodies pass within 1 astronomical unit of the Sun per year, and if most are small and faint, then the job of modern surveys is to raise the fraction we detect from a few percent to a sizable piece of that flow. The Rubin survey will be the keystone, but not the only one. Smaller wide-field facilities can run targeted search modes toward the solar apex and anti-apex, where the yield is expected to concentrate. Early alerts will let large telescopes obtain spectra and high-resolution images, and will let heliophysics imagers catch the dust environments for those objects that brighten quickly. If a detection occurs soon enough and the speed is moderate, mission concepts like the European Comet Interceptor or proposed rapid response spacecraft could attempt a close pass. Population studies show that reachable targets exist at a rate of about 1 to a few per decade for a craft with aggressive propulsion and a prepositioned flight plan. How often will we meet something like 3I/Atlas specifically, meaning an active comet with a nucleus hundreds of meters to kilometers across and an interstellar speed comparable to or greater than 50 kilometers per second at infinity? On present models, the answer is sparse, but not vanishingly so. The same Gaia-based arrival rate analysis that yields 7 within 1 astronomical unit per year also infers a much lower number density for clearly cometary interstellar bodies, the 2I/Borisov class, relative to Oumuamua-like objects. That points to discovery opportunities roughly once per decade as survey sensitivity climbs. In that frame, the appearance of 3I/Atlas within a decade of 2I/Borisov is not an outlier, but a reasonable draw from a small sample, boosted by the steady improvement of all sky searches. You can also reframe frequency by galactic provenance. The Milky Way thin disk supplies the bulk of visitors. These are the familiar motions of nearby stars that share the Sun's broad rotation around the galaxy. A smaller slice arrives from the older, dynamically hotter thick disk. A tiny fraction comes from the halo, and an even smaller fraction is unbound to the galaxy. Those categories are not just labels, they carry testable predictions. Thick disk visitors should, on average, move faster and be older. Unbound visitors would be extremely fast and extremely rare. 3I/Atlas, with its high interstellar speed and possible thick disk ancestry suggested by population modeling, sits exactly where the tail of the distribution says it should. The rarity of that tail explains why objects with comparable speeds will be uncommon in any single decade of observation, but not impossible in a generation. Finally, do not confuse the rate of arrivals with the rate of announcements. The headline discoveries depend on survey uptime, weather, moon phase, cadence, and community follow-up. A fast object that hugs low elongations during a lunar bright time may slip by. The practical lesson is that frequency questions have two answers. The physical rate in space is set by galactic dynamics and gravitational focusing, and it is already high. The observed rate on Earth is set by how and when we look, and it is poised to climb. If the legacy survey of space and time delivers even the conservative figure of roughly 1 to 2 interstellar objects per year, the community will accumulate a dozen to a few dozen solid cases across the next decade. If the population is steeper or brighter than assumed, the yield could be far larger, perhaps dozens per year in the best case. Either way, the interval between confirmed interstellar visitors is shrinking from years to months as the instrumentation improves. That is the real answer to how often we are visited. Often already and soon, measurably often. The upshot for Night Science Stories is simple. There is nothing exceptional about the arrival of an unbound body. The exceptional part is our growing ability to spot them before they rush past. A flow on the order of several per year within Earth's orbit is already a given from stellar kinematics. A detection rate of many per decade is a reasonable near-term expectation. 3 I/ATLAS is a bright example caught in the act. With the next generation surveys, it will not be alone in our catalogues for long.